a very rudimentary introduction to a topic called linear programming, very basic introduction, and the idea is to introduce what is known as the primal dual method. So there is some background. Okay, so for designing approximation algorithms. So there is a large class of algorithms for approximation algorithms. When is an approximation algorithm deployed for a problem? When you cannot get a polynomial time exact algorithm for the problem. So when the problem is too hard to be solved exactly in polynomial time, we look for approximate solutions. Fine. So one of the paradigms of design, see if you have done a course in algorithms, you would have seen things like divide and conquer, dynamic programming, greedy, these kinds of classes of algorithms, right? Primal dual algorithms form an advanced, slightly more advanced algorithm design methodology, which is actually not very intuitive, but it gives a mechanical recipe for designing algorithms. If for certain class of problems which can be expressed as a maximization or a minimization problem, problems which are maximization or minimization problems where you have to optimize something subject to certain linear constraints. Okay. So instead of let's look at how many of you have seen something on linear programming so far. So just raise your hands those who have seen linear programming. Okay. How many of you have seen the notion of a dual of a linear program? Okay, that's also a fairly large number. How many of you have not done anything on linear programming? Let me see. You have not done anything on linear programming. Okay. So we will anyway, I will do all the basics which is necessary to understand it. If you are completely familiar with it, you may not get much, but I hope something will be new. Okay, so let's start with some simple plain geometry. So let's try to look at this equation. What is the equation? So right now I am talking about the two-dimensional plane R2. R2 means what? The plane. Okay, the plane. Okay, so this lecture doesn't depend on anything that was done so far. So what is the equation to the line through the origin perpendicular, this is symbol is for perpendicular to the point or the line joining, perpendicular to the line joining zero, 0 and say 1, 2. Let's ask a simple school geometry question. What is the equation to the line through the origin perpendicular to the line joining 0, 0 and 1, 2? How will you get this? How will you get this? Yeah, so finding the equation is simple. So, okay, if I take 1, 2, right? I look at the point 1, 2, okay. So I am going to look at this line, right? I am interested in this line, correct? I am interested in points on this line. Now, how will you find out the locus of this line? You take any vector here, what is, now this vector has, let us say, coordinates xy, correct? Any vector here will have some coordinates xy. I want to find out those vectors xy or points xy whose dot product with this vector 1, 2 is 0. So you have the equation dot product of 1, 2 dot product xy equal to 0 or x plus 2y equal to 0. isn't it? The dot product of this vector 1, 2, dot product of the vector 1, 2 with any point xy. I want those xy points, so it's the dot product of 1, 2 with xy is 0. You know that two vectors are perpendicular if and only if their dot product is 0. Okay. So this, the function, if you look at the, if you think of this function, linear function, x fxy equal to x plus 2y, this is what is known as an equicontour for this line. That means every point on this line will have this function's value go to 0. So you can think of it as a line, or you can think, if you think of the function f x plus 2y, on each point on this line, the function f x y equal to x plus 2y will be equal to 0. Is this very clear? So now let us generalize this question. So what is the equation to the line through the point x naught y naught, let us say, through the point x naught y naught, let us say perpendicular to the line joining 0, 1, 0, 0 and perpendicular to the line, which one is a good one? This one, okay. Perpendicular to the line joining the origin and let us say the same point, let us have points 1, 2. There is nothing special about 1, 2, because if it is AB, if this instead of 1, 2 I was looking at an arbitrary point AB, what would I get? What will be the equation to this? Ax plus by equal to 0. So that is the standard equation to the line through the origin, right? So any line will be perpendicular to some AB. So Ax plus by equal to 0 represents the set of points which are perpendicular to the point, the line joining origin with the point AB. Is this very clear? Okay, that is how you have the equation to an arbitrary line through the origin. So each line is defined by a vector perpendicular to the line through the origin. So let us ask this question. Now suppose I want to find out the equation to the line through the point x naught y naught. You can put 1, 3, 1 or 4, 2 something, it does not matter. So I want to find out the equation to the line which is perpendicular to this vector 1, 2. Okay, it is not 1, 2 now, this, so this vector will be x naught plus x naught y naught. So this vector will be 1, 2, correct? Now I want to find out that line which is perpendicular to the vector 1, 2. Okay, so I want, see you can think of the line joining 0, 0 and 1, 2 as a vector, correct? So if I place that vector here, it will look like this. So this vector will, when I place it here, it looks like x naught y naught plus 1, 2, right? And I want to find out, see this is nothing but shifting the origin to the point x, so it's a translation of the origin to the point x naught y naught. So the solution to this problem is obtained by doing nothing other than translating the origin to the point x naught y naught. So you just place this line there, that is it, correct? How do you get that equation to the line? So again the idea is very simple. I want if I look at any point xy here, the line joining x naught, y naught and xy should be perpendicular to the vector 1, 2, correct? So the equation is obtained by, so dot product of 1, 2 with any point here is x minus x naught, y minus y naught equal to 0, correct? Agreed? Agreed? So, what is this? This is, that is x minus x naught plus 2 into y minus y naught equal to 0, or x plus 2y equal to x naught plus 2y naught, which will be some constant, right? That x naught plus 2y naught will be some constant. So, you get the equation to the line as x plus 2y equal to c. This is very basic school geometry, just to remember this. Okay. Is this clear? No questions about this. Now, so what I find is that, or otherwise, the function f(x,y) equal to x plus 2y will have the same value c is equal to x naught plus 2y naught on any point on this line. Okay, on the line, on this line. So, basically any point on this line. So, okay. So, what is the geometric intuition we have? A linear function will have the same value along. See, if I fix a point, okay, there is a line along that point. So, if I fix, this is just x naught y naught equal to 0, 0. This is a special case of this is the first case is a special case of the second case where x naught y naught is chosen as 0, 0. So, any line is actually defining a function, or any line is actually defining the what is known as the equicontour of a function. That means a set of values of a linear function, the set of points of where a particular linear function takes the same value. Is this very clear? Is this very clear? Okay. Is this very clear? So, for example, okay, so now is the other way true, like if a linear function has the same value at 2 points, can you say that the 2 points, suppose a linear function has the same value at 2 points, can you say that these 2 points are parallel to this? Is that true? See, right now I saw that a linear function x plus 2y has the same value along this line. Now, if I put a point x naught y naught, if I put a point say x naught y naught, if I draw this line parallel to this through this point, it will still have the same function, same value, but not the same value as this, it will have a different value. Here it will get 0, here it will get what value? C, which is x naught plus 2y naught. In general, if the point which the perpendicular is the vector is a b, then you will have a x naught plus b y naught will be the c value, correct? So, can we always say that? Now, if you take 2 points, see, okay, or let us try to derive a criteria. When are 2 points having, let us ask this question, okay, write down the question. So, when can we say what is the condition? What is the condition for, can we say that say x y and let us say x naught y naught give the same value to the function f x y equal to x plus 2y. What is the condition for 2 points x y and x naught y naught to have the property that the function, linear function x plus 2y evaluated the same value at these 2 points? What can you say about these two the points x y and x naught y naught? Or let us put this as x1 y1 and x naught y naught. What is the requirement? So, the requirement is that x1 plus 2y1 should be equal to x naught plus 2y naught, correct? That is x1 minus x naught plus 2 into y1 minus y naught should be equal to 0, correct? Which means that if these 2 points have the, see the values on this point and this point are the same, then if this is x1 y1 and this is x naught y naught, then this vector has to be perpendicular to, see this is telling what? This, that is x minus, so 1 2 and x1 minus x naught, y1 minus y naught must be perpendicular. So, the line joining the 2 points has to be perpendicular to the vector 1 2, or otherwise the line joining the 2 points should be on collinear to, the line joining the 2 points should be, the vector joining the 2 points should be along this line. Is this very clear? Is this very clear? So, that is what this says, right? Because the vector joining x naught y naught and x1 y1 should be perpendicular to the vector 1 2, that is what this says. Is this very clear? Very basic geometry. Okay. So, with this very basic geometry, let us try to understand linear programming. So, linear programming is about giving, is about trying to find the value, find a point where a linear objective function gets a maximum or minimum value subject to certain linear constraints. So, let us try to see what this means geometrically. Okay, so let's review what we have done so far. So, if I look at this line, so suppose abstractly say this is a point AB, all points perpendicular to the vector AB along this line, okay, will have Ax plus By equal to what will be the value of the function on all if I evaluate this on these points? It will be 0, right, because you are perpendicular to AB. Now, if I go here, it will be, take any point here, say take any point here x naught y naught, all points here perpendicular parallel to this line, pass on this line parallel to this line passing through x naught y naught will have the same value Ax naught plus By naught and so forth. That is what our analysis shows. Is this very clear? Is this very clear? So, what happens is that depending on the value of Ax naught plus By naught, when you go this way either the function continuously increases, when you go this way the function continuously decreases, or it might be the other way because A and B are negative, then when you go the picture will change, that is all. Okay. So, to the left or one direction the function's value, if I draw lines parallel to this, on the left side all these points will have the same value, but that would be less than this. On all points along a line that is on the right of this, the function's value will be the same. Okay. And if I travel this way, for example, the function's value might keep increased. Now, the increase or decrease depends on the nature of the coefficients, because if the line looks like this, then what happens? So, this is the increasing direction, this is the decreasing direction and so forth, right? Okay. Fine. So, this is the background we should have. This is all the background we should have. So, now let us look at a linear program. Let us take a simple example for a linear program. So, maximize, so this is something called a linear optimization. Expressed as a linear program. So let us say maximize x plus 2y subject to, see if I am asked to maximize x plus 2y, I can go to infinity and get larger and larger values, right. The problem is interesting when I have some constraints, and the constraints are also linear, subject to, let us say x plus y 2y is less than or equal to 4. So, typically I will assume that x greater than 0, x, y greater than 0, that is typical in linear programming problems, although this is not mandatory, but the standard form representation typically assumes x greater than 0, y greater than 0, we will stick on to that. So, x plus say 4y less than or equal to 6. Suppose you look at a linear program like this. Oh, I do not want to choose x plus 2y, I will rather choose x plus y, let us say, for reasons which will be clear after some time. So, let us try to look at the geometry of this. So, what is this saying? This, let us try to interpret this. Okay. So, now x greater than or equal to 0 is this region, y greater than 0 is this region, right. So, we are looking at the first quadrant, that is what these constraints are saying. Now, x plus 2y less than or equal to 4 means what? Again, let us plot x plus 2y equal to 0 becomes this line, right, that we have seen. So, I need to go up to 4. I want to, the constraint region, the region where this constraint applies if I put this grid. Now, what happens when x plus 2y increases? So, can you give me the line which makes x plus 2y equal to 4? 0? So, one point is 4, 0, right? This is one line, and if I get one point, that is enough, because on all if I look at this, so x plus 2y equal to 0 goes this way. So, x plus 2y equal to 4 will be, from what we have seen, it should be something parallel to this passing through this point. Pardon? No, 4 comma 0 is this, right? 4 comma 0 has x plus 2y equal to 4, right? Okay. The y axis point I got wrong. Okay. So this should go to, from here it should go to like this, yes, I agree. So, the feasible region, this inequality says that you should be looking at for a solution. Now, x greater than 0, y greater than 0 is already there. That means you should be looking for a solution which is below this line. Is this very clear? Now, what is the other constraint saying? So, this says that x plus 4y less than or equal to 6. So, this is saying 6, 0 is 1 point. Okay. The other one? Pardon? 0, 1.5. Yeah, so okay. So 0, 1.5 or let's try to get a better point. I'll change this. X plus, let's put 3y less than or equal to 6. Then that 1 point sign goes away, right? So 1.60, this is 0, 0, 2. I'm still not happy. That's getting too far. So, okay, let's have the same thing, 2y less than or equal to 6. So, this way, x plus 2y is also a problem. So, 4y let's have. So, I'll have 1.5 here. This is 3 by 2, right? Huh? X plus 6y equal to 0 will make life a little, okay. So, what will happen now? X equal to 6 and this will be 1, right? Yeah, okay. That is a better picture. Okay. So, now my feasible, what is the region which is satisfying these two constraints?
0, 1.
This is 0, 1. What is this point? This is 3? No, according to my picture it is 3, but actually it could be something else. I'll have to solve this, right? So, what is it looking like? X plus 2y equal to 4 and x plus 6y equal to 6 gives you, after subtraction, this is 4y equal to 2. So, y equal to half. So, this point actually y is equal to half. And what is the x value for this? X should be equal to 3. So, this point is actually 3 half. Okay. This point is, although the appearance doesn't look so, the point is supposed to be 3, 2, 3, 1 by 2. Okay. So, now let's zoom this picture and think of this something like this. So, there is a point 3, 1 by 2. This is something like this. Here you have two constraints, one constraint running like this and another constraint running like this, right? And this point is 3, 1 by 2. What was this point? 0, 1. Is it? Yeah, this is 0, 1. This is 4, 0 and this is 0.0. Okay. So, this is the constraint region. This is the region where I am searching for a point. Okay. This is a region where I am looking for a point. I will use a different color. Now, what am I trying to do here? I found this region and I have an objective function x plus y, right? X plus y looks like what? Okay, let's look at plot x plus, what are the points where x plus y equal to 0? X plus y equal to 0 along this line, right? Okay. So, x plus y equal to 0 along this line. Now, x plus y's value will be the same. This is something which we have seen. X plus y will have the same value along any line parallel to this. So it will keep increasing, either increasing or decreasing as you draw, that depends on the coefficients. It will keep either increasing or decreasing. Okay. So if you go here on this line, on every point on this line, the value of x plus y will be the same. It will either be greater than the value here or less than the value here, depending on the coefficients actually. So for 1, 1, of course, if you draw on this line, it will increase, right? Now the point is, this is a corner point. So how will I try to maximize this function, x plus y? I will try to draw a line, okay, parallel to this as much to the right till a point is reached. If I shift the line any further, I will go out of the feasible region. So what I am essentially trying to do, if you want to solve it using scale and pencil, what you try to do is you try to draw a line parallel to x plus y equal to 0 in this region to the extent possible, such that there is at least one point on the line which is in this region. Is this very clear? Okay. And now if you shift a line along a region like this, right, where will you hit the maximum? It should hit the maximum at some corner point. Okay, it should hit the maximum at some corner point on this. It should hit the maximum at some corner point of the, and how do you find out the corner points? See, this is a system of equations in two variables, right? So two equations will define a point. Okay, how many equations do you have? Actually not two, you have 4 equations, right? You have 4 equations. Okay. So how many corner points will I get? 4, choose 2. I can take, see, any 2 of these 4 equations will define a point. For example, x plus 2y less than or equal to 4 and x equal to 0 will define a point. 2 linearly independent equations. Assume that all these constraints are linearly independent, otherwise there is something called degeneracy. One of the constraints will be redundant, in the sense if one constraint is expressed in terms of the others, we can remove that constraint. So for the time being, let us assume that the constraints are independent. Then any 2 constraints will define a point. Okay. And what this geometry tells us is that a maximum can be obtained always at a corner point. Okay. Is this very clear? Let us try to generalize this idea. So the simple geometric intuition, let us try to generalize and see. Now, is this very clear? Is this very clear? Some problems? No. So now let us look at the framework of a general linear program in n variables and m equations. Let us think of it. Okay. So you typically have something like this. Minimize, let us say, C1 x1 plus C2 x2 plus Cn xn subject to the constraints. Typically the way it is written is a11 x1 plus a12 x2 plus a1n xn less than or equal to b1. Okay. So first of all, before getting into this, let us go into 3 dimensions and see what this is saying. Suppose you look at a point in R, see if you look at R3, again something like Ax plus By plus Cz equal to 0 defines what? You look at the point ABC, correct? You have 3 dimensional axis. You look at a point ABC. I am looking for a plane which is perpendicular to the normal vector ABC. That is the equation Ax plus By plus Cz equal to 0. Same ideas work. Same ideas work. So on the upper half of the plane, the functions, see if you look at any point, see on all points on this plane, the function ax plus by plus cz has the same value 0. If you shift the plane upwards, then the value keeps increasing. For any point on a plane, if you shift the plane below, the value of ax plus by plus cy will be the same, but on that plane. So basically, ax plus by plus cz equal to 0 defines a plane. Ax plus by plus cz equal to k defines a plane which is parallel to this, and any point will lie on some plane parallel to this, right? Okay. So that's essentially the same ideas work, except that if you are optimizing a linear objective function in 3 variables, instead of shifting a line in the feasible region, you will be shifting a plane in the feasible region till it touches one of the, till you cannot shift further, beyond which the plane will entirely lie outside the feasible region. Yes? Oh, okay, this should be greater than or equal to inside. This is okay, right? So normally, if you are trying to minimize an objective function, the constraints will say that something is greater than, right? Because minimize x plus y subject to x less than 5, y less than 10 is easy because it goes to infinity, right? Minus infinity, minus in infinity. So, right? See, if you want to minimize x, minimize the value of x, let us say 3x, subject to the constraint that x is less than or equal to 5. Minimize x subject to the constraints x less than or equal to 5 is going to infinity. X equal to minus infinity gives you. So what typically happens is that you put the constraint that all x values are greater than 0. You will have some constraint say that some linear combination of x has to be at least this, and but still you have to minimize a linear objective function. That is entirely symmetric with this. Okay. Now, so let us write down this. You will have some typically some m constraints. A m n x n along with constraints x1 greater than or equal to 0, x2 greater than or equal to 0, xn greater than or equal to 0. So how many constraints do you have? So for simplicity, I will assume that these are independent constraints. In fact, I will assume all the constraints are linearly independent constraints. If you do not understand what linear independence is, forget about it. In the sense, one constraint does not obtain from some other, cannot be expressed in terms of some other constraints. For the time being, let us not get into it. So now, in fact, all constraints are linearly independent. If all constraints are linearly independent, what is the advantage? If you take, how many equations are there now? N plus n. Now there is some theory which tells you that if you have n plus m constraints, n of these constraints will define a point. See, if I pick any n of them, then those will fix the values of x1 to xn. So assuming that the constraints are linearly independent, any n of them will fix a point on the what space? Space of, what is the space on which the solutions exist here? R raised to n, right? So if you take n equations in n variables, that will fix a point in R raised to n. So how many points can you get out of this by taking n from this? So okay, so there are n plus m choose n corner points, one of which gives the optimal value of the objective function, which typically what you call this okay. So, although this looks like a continuum problem, you are trying to search for a solution in an infinitely large space. If I want to look for an optimal point for this that maximizes this function in this region, the problem looks formidable because this is a space with infinitely many points. Okay. But the fact that an optimal solution should occur on one of the corner points make the problem a discrete problem or a combinatorial problem, because you need to search on a finite search space. This is what makes the problem immediately in NP, for example, because given a point you can easily check whether, given a point and the set of equations, you can easily check whether this point is the intersection of those planes. So, this point is defined by these lines, and then you can check whether the objective value of the function is C at that point, and this kind of things is easy. So, I will not again go into the business of NP right now, because that is not our theme. But the important thing to understand here is that I want to find a point xy in this region, this continuous region where a function gets maximum value. This is a continuous problem. This is a problem with infinitely many solution points. Now, the fact that the optimal solution can be obtained at one of the corner points suddenly changes the problem into a algorithmically solvable, programmable problem. You take the equations, take n out of them, solve them, you get a point, you test it out, you choose. If you take n plus m, choose m points which are corner points, you know that one of them will be optimal. So, take the maximum. So, you get an algorithm for this, although the algorithm does not run in polynomial time, because n plus m choose m can be very large. Is this very clear? Okay. So, this although is a continuous mathematics problem, certainly it can, this observation that the optimum should, there should be a corner point optimum, changes the problem into a algorithmically solvable question. This is the first point to understand. And therefore, linear programming, it turns out that fact is that if assuming that the constraints are all rational numbers, linear programming problem can be optimally solved So, this method, the method which I outlined here, requires you to look at n plus m, choose n points. There are better algorithms which reduce the search space and find an optimal solution in polynomial time. So, therefore, linear programming becomes solvable in polynomial time. Now, for those math people, why should you have a maximum? Why should you have a maximum here? That is because the region is a compact region. So, a continuous function will attain a maximum on the compact set. Okay. So, okay. So, maximum will always exist if the constraints are less than or equal to. So, the bounded regions will be compact in this case. All right. So, that's about introduction to linear programming, which I wanted to say. Now, is this very clear? It is very quick and sort of peripheral, in the sense we do not look deep into the theory. I just draw some pictures and explain what is going on, but I hope some intuition is there with solving such systems. Now we will never solve these things directly. We can assume that there is some solver is given for linear programming. The fact to understand is linear programming black box is always obtained. But the problem is, for the example, this particular linear program, the optimal solution will turn out to be 3 1 by 2. This is not good enough. For example, if you try to solve the vertex square problem, you will get a linear programming formulation. You have seen this, isn't it? But the problem is the formulation gives you a integer linear programming formulation, whereas what you know to solve in polynomial time is fractional optimal solution. So then you have to round off the fractional optimal to get a simply rounding the fractional optimal need not always give you integral optimal. Just making 3.2, because see, this is optimal doesn't mean that if I make this nearest integer point, if I pick the nearest integer point, then it may not be the here. Okay, in this case optimal is 40. Okay, in some other case, okay, in that case, so 40 it happens to be integral. In this particular problem, yes, the maximum has integral solution, but it may not always have integral solution. Have you seen vertex square instance where there is no integral solution? See, the vertex square problem, you are done in class, right? You are done in the class, right? Have you seen any instance where the integral solution does not exist? Something went into my head. So if you look at this graph, let's try to formulate vertex square this way. What is the vertex square formulation for this? Yeah, this is half, we have already seen, right? So the problem is, if I look at this as vertex number 1, vertex number 2, vertex number 3, so minimize x1 plus x2 plus x3 subject to x1 plus x2 greater than or equal to 1, x1 plus x3 greater than or equal to 1, x2 plus x3 greater than or equal to 1, x1 greater than or equal to 0, x2 greater than or equal to 0. This is your vertex square formulation, right? I hope you have done the vertex square, right? What is optimal solution to this? Yeah, 1 by 2, 1 by 2, 1 by 2 is optimal solution. So this is not a vertex square. This is the problem with linear programming. I will get in polynomial time that 1 by 2, 1 by 2, 1 by 2, from which when you round off to get a vertex square, what happens? Your solution becomes approximate. And probably they would have, she would have done the bound on approximation, right? It's shown to be 2-factor approximation, right? Okay. So this is one way in which linear programs are used in algorithm design. You do a linear programming formulation. This is not, what you do is an LP relaxation of the original integer linear programming formulation, and then solve the LP relaxation optimally using linear programming algorithms, and then round off the solution to get an approximate solution for the integral linear program. This is one way of using this. We will see another way of using this. For that, we need to introduce the notion of the dual of a linear programming, for which unfortunately there is no simple geometric interpretation. So let us try to look at the notion of the dual of a linear program. Okay. So let us start with the linear program this way. Suppose I multiply this equation with some variable y1, with this some variable y2, this with some variable ym. These variables sometimes are known as dual variables. I am going to multiply each equation with a variable which I assume y1 and y2 are all positive. Okay. Is this very clear? So you are given a linear program like this. This is what is given to you. Okay. Now, what I originally wanted is, okay, let's fix our objective. So, given a linear program, problem, let us say this is your linear programming 1, the formulation here. How to get its dual linear program. This is a very mechanical procedure. Okay. And instead of stating the dual and then saying that this is the dual, I am trying to derive the dual here and see why how that formulation comes. So, right now just follow what I am trying to do. I just multiply each of these constraints with, this is very mechanical, does not require any geometry, algebra, some basic symbolic manipulation suffices. So, if I multiply each of these equations with this, on the right side what do I get? I will get b1y, b2y, etc., right. So, let's multiply with this and sum all these equations. Let us call this equation number 1, 2, m equations are there. So, 1 plus 2 plus m gives you what? So, I will start with the right side. What is there on the right side? So, this is b1 y1 this is less than or equal to, correct? Now, what is that you have here? So, let us put this as x less than or equal to a11 x1 y1 plus a21 x1 y2 plus a m2 m1 x1 ym. This is the first term, right? Okay. So, this I can write as plus, okay, plus, now what is the simple way of looking at it? I want to take something outside from this. So, what I will do? I will take that x1 outside and write this is less than or equal to x1 times a11 y1 plus a21 plus a21, this is not a vector or anything, just plus, I just wrote it this way, okay, plus a21 y2 plus a31 x1 into, okay, a11 y1 plus a21 y2 plus a31 y3 plus 21, correct, a m1 y m. This is this term. Okay, is this clear? I just rewrote this first term plus x2 times, now the second column, right? You will get the second column times x2, correct? So, a2 21 y1 plus a22 y2 plus a 12, yeah, 12 y1 plus a22 y2 plus a m2 ym times x2, correct? So, what is the last term? Plus xn times a1m y1 plus a2m y2, no, 1 m, a1m and a11 y1 is correct, no? A1n, yes, A1n, correct. A2n y2 plus AMN ym, okay. This is what this is. Okay. All right. So now, let's try to get a condition for this to be less than this. I want, suppose when does this become? What is the requirement? What is the condition? For this, what is the condition needed for this sum to be less than or equal to C1 x1 I want to get some linear system of constraints which will ensure that this sum is less than or equal to C1 x1 plus C2 x2 plus Cn xn. So, what is that linear system of constraints? If this is less than or equal to C1, this is less than or equal to C2, etc., then this sum will be less than or equal to C1 x1 plus Cn xn, right? So, that gives you the dual, what are known as the dual constraints. So, from this we derive okay. So, what we do is, if I impose the constraint, so if y1 to ym satisfy, what is the constraint required? So, equation 1 will be, so let us say this is condition B. So, B will hold true, if B will hold if what? Y1 to ym satisfy, y1 to ym satisfy. So, this sum should be less than or equal to C1, right? See, I want this x1 into this plus x2 into this plus x2 into this less than or equal to C1 x1 plus C2 x2 plus Cn xn. If for that to happen, I require that this should be less than or equal to C1, this sum should be less than or equal to C2, this sum should be less than or equal to Cn. Is that clear? That's straightforward, right? So, I write down this constraint. So, this if y1 to ym satisfy what? Yeah, a11 y1 plus am1 ym less than or equal to C1, a12 y1 plus am2 ym less than or equal to C2, an1 y1 plus a m n y m less than or equal to C n. So, now what I have is how many constraints? N constraints. So, here I started with m constraints. Okay. So, let us try to again clarify what is happening. I introduce some new variables in the first place. I introduce some new variables. So, given I had originally been given a linear programming formulation, minimize C1 x1 plus C2 x2 plus Cn xn subject to these constraints. I introduced some variables y1 to ym and looked at the sum b1 y1 to bm y1 and showed that the linear function b1 y1 plus bm yn will always have value less than or equal to this sum, which is written here, which will be less than or equal to C1 x1 plus Cn xn, provided y1 to im which I have introduced satisfy these requirements. Is this very clear? So, this gives a linear constraint system for y1 to ym, okay, and these are known as the dual constraints. So, let us try to write down this. Okay. So, let us write down the consequence of this. So, what should be the dual? What should be the dual linear programming? I have the constraints. What should be the dual objective function? b1 y1 plus bm y1, right? Now, any solution, okay. So, the value of any value of the objective function the linear function b1 y1 plus b m ym, let us call this constraint C, subject to C and of course, the non-negativity constraints I put in the first place that ym is greater than 0, right, and will always be less than or equal to the value of the linear function, that is what we proved, right. Subject to the constraints. May I rub this off? So, subject to the constraints, subject to the constraints, okay. The value of any solution, the value of the linear function b1 y1 plus bm ym subject to these constraints, will always be less than or equal to the value of c1 x1 plus cn xn subject to the constraints A. Okay. So now think of a linear function. So suppose look at, you put the requirement, okay, minimize subject to this. Okay. See, any solution for this subject to this will be less than or equal to any solution to this subject to this. So in particular, the maximum of, sorry, I want to maximize this. The maximum of this will always be less than or equal to the minimum of this, right? Any solution to this subject to these constraints will be less than or equal to any solution to this subject to these constraints. Okay. So if that is the case, then the maximum value of this can never exceed the minimum value of this. Is this very clear? What we have shown is called it's called some theorem, weak duality theorem. This is known as the weak duality theorem of linear programming. And for a given minimization problem with what is known as the standard form formulation of the constraint system, this way, this is the dual objective function with the standard formulation of the constraint system on the dual variables expressed with less than or equal to constraints. So if the primal is a minimization problem, its constraints will be greater than or equal to what is known as a standard form expression. Now for this case, the dual will be minimization problem, minimizing an objective function, where the objective function is obtained by this B1 to Bm, okay, and the constraints will be less than or equal to constraints. We will have the C1 to Cn on the right side of the constraints, and this comes from this requirement. See, this comes from the fact that you are trying to, I want to get the dual's value less than or equal to this. Naturally, these constraints come on these. Is this very clear? That's how you formulate the dual. We will see some examples. Now, there is what is known as a strong duality theorem of linear programming, which tells that there exists a solution. If you are not working with integral requirements, if you allow real numbers, there exists a solution. In fact, a rational solution will exist such that there is a value of x1 to xn and y1 to im such that this value and this value is equal. There exists, given a formulation of this kind, if ever a solution exists, for both the primal and the dual, then there is a solution, there is a set of values for x1 to xn and y1 to im such that the value of this objective function for those values of y1 to im and the value of this objective function for x1 to xn will be the same. That means both are optimum. Both are optimal. Is this very clear? Now, before it's almost time, but before I stop, I just want to ask one question. When you look at an optimal solution, look at these expressions. Okay. If you look at this expression, now let's look at this expression a little more carefully. May I rub this off? This should be in your head. Okay. Now, we will see some exercises doing primal dual formulations tomorrow, but one should be clear about these formulations. This is a very, very powerful system. When we see, I will see some algorithms designed. We will see that some algorithms can be designed on this. Depending on the availability of time, I will discuss this. Definitely, I will do at least the vertex coerce algorithm based on primal dual formulation. Okay. So, when is equality? Suppose so x1, x2 to xn is an optimal solution. I will finish in 10 minutes. to the primal and y1 to ym an optimal solution to the dual. So, suppose I look at an optimal solution for the primal and optimal solution for the dual. In that case, what can I conclude? This value is equal to this value, right? That is C1 x1 plus Cn xn is equal to B1 y1 plus Bm y. Now, if that is the case, what can I say about these equations? What, see this, if x1 into this plus x2 into this plus xn into this is equal to this, what can I conclude about these values? See, x1 into this plus x2 into this plus xn into this must be equal to this. Then what can I say? Component wise they are equal, right? So, if x1 to xn is an optimal solution for this and y1 to ym is an optimal solution to this, then I can surely see that x1 into then C1 x1 should be equal to a11 y1 plus a21 y1 plus y2 plus a m1 ym into x1, right? This must be the case. So, what can I conclude? So, this just not for ai, for all of these this will hold, right? So, I am going to write for each I xci xi okay, cj xj will be equal to a1j sorry aj1 y1 plus aj2 y2. This confuses people more, I suppose. So, let us write C1 y1. So, C1 x1 should be equal to this should be equal to a11 y1 plus a21 y2 plus a m1 ym times x1. Similarly, I have an equation. So, similarly, I should have C2 x2 should be equal to a12 y1 plus a22 y2 plus a m2 ym x2 and etc. I will get a sequence of equations. Now, this equality gives you what? I know that x1 is greater than or equal to 0. So, what can I conclude from this? So, when there is a solution y1 to ym and x1 to xn satisfies this this is equal to this. When that happens, then, so what can I say? This is equal to this. What can I conclude? Either x1 equal to 0, this implies x1 equal to 0 or a11 y1 plus a m1 ym equal to 0, correct? Similarly, from this I will get either x2 equal to 0 or a12 y1 plus a m2 ym equal to C2. You will get a sequence of conditions like this. Pardon? Or equal to C1, sorry, is equal to C1. What are these conditions called? These are known as complementary slackness conditions. these conditions are known as, you will get a sequence of m conditions. These are known as the dual complementary slackness conditions. Similarly, if I rewrite this expression and equate this, I will get a sequence of primary complementary slackness conditions. That is also easy. So, this expression I can rewrite as, this is y1 into, I can rewrite this expression as y1 into, okay, y1 into what? a11 x1 plus a12 x2 plus a1n xn plus y2 into a21 x1 plus a2n xn plus ym into am1 x1 plus amn xn, correct? This I can write this way also. So, from this I will get a sequence of conditions. What are those conditions? This should be equal to this, correct? This should be equal to that, and so forth. So, the second term here is plus b2 y2 plus, that is how your expression looks like. So, what is the primal complementary slackness conditions I get out of this? b1 y1 should be equal to y1 into this, correct? From this I will get either y1 equal to 0 or this sum should be equal to b1. So, when the solution is optimal, there is a lot of structure with these simple linear equations. Okay. Similarly, we get dual conditions, sorry, these are known as the dual either the dual variable is 0 or the primal equations, either the okay, I do not know whether this is dual slackness or primal slackness. Somebody, what is primal, what is dual, I forgot. But the conditions are the correct, except that which set of conditions are known as primal conditions, which conditions these are called, it does not matter, otherwise take it the other way. Yeah, but this there is some name given to this and some name given to the other. So, let us call it simply slackness conditions. There is another set of slackness conditions you get. What are those? So, either y1 equal to 0 or a11 x1 plus a12 x2 plus a1n xn equal to c1. Similarly, you will get y2 equal to 0 or a21 x1 plus a22 x2 plus a2m 2n xn equal to c2 and so forth. Equal to, sorry, this is b1, this should be b2, yes, and so forth. So, these are all very, very simple facts we get, although when we actually work with the problem, this x1, y1, x2, xn, etc. can become very confusing. If you look at the equations, if you write it down straight away this way, it is very easy to find these derive these slackness conditions as well as the primal, the weak duality theorem. Although strong duality theorem is not easy to derive. Actually, we tried to write a simple and humanly understandable proof for this theorem, which can be done, in a course, for example, undergrad BTech course, and a person end up writing a thesis which is this size. It's there on the net. If you go to my homepage, the MTech student has written a self-contained proof for this, but that's not small. We tried to make it small. There is no simple proof for the strong duality theorem, that there exists a solution which matches optimal solution which this and this are the same. That's not easy to get. But otherwise, any solution to this should be less than or equal to any solution to this is actually very easy to see, and when there is an when equality holds, these conditions should hold is also equal to C. So this is what textbooks give you as complementary slackness conditions, and this is the proof of what we have done is the proof. See, what we have learned is, given a primal formulation, how to write down the dual formulation. We have seen the weak duality theorem. We have seen that for any solution which satisfies the primal, any solution for the primal and any solution for the dual, the value of the solution, primal solution should be less than or equal to value of the dual solution. And in particular, if primal is optimal and dual is optimal, the values should be equal. When the values are equal, naturally equating these expressions, we will get the complementary slackness conditions. Okay. So this is just symbolic manipulation, but I want you to work this out a little bit and come tomorrow, because we will be looking at problems, formulating them. For example, we will try to write down the dual of vertex cover problem, set cover problem, and stuff like this. So try to get some familiarity with this, and we will continue with this in the next class. Okay.